I mean, he was on like, and they were driving, talked about how they were driving around the dams with these giant antennas on, trying to like map out signal ranges. It was crazy.
That's crazy. This I've been on that for this time.
I think that's kind of accurate.
Somebody have their laptops today? Does somebody does not have their laptop? Do you not have a laptop? That's a problem?
The processor like melted.
Okay.
So,
You kind of look, you know, I think you can go and check out laptops from the library.
right now?
Well, not right now, but in general.
Okay.
Can you try for next time to come with a laptop?
Yeah, I'll try.
Okay, I mean, I understand if something's wrong with your laptop.
I've got a Raspberry Pi.
Yeah.
You know, use like
Yeah, I actually don't have Raspberry Pi too.
But Raspberry Pi and what? I need
Yeah, we got
I need
a
people to
monitor.
work right now, give you a monitor and keyboard and.
I don't know.
There's actually a kid that did that in my computer. He's on a monitor.
What do you do? That's awesome. Large monitor?
Yeah.
I really don't have a
Standard
monitor.
work, so he's plugging the monitors to the side of it.
When you think about it, you can actually power the Pis off like those like power little power packs you use to charge your phone.
It's that's why, yeah.
You just need a cable for monitor.
And you can buy the touchscreen whatever things for like $30 or
They're
like.
super weird.
Yeah,
What are you talking about touchscreen for the Pis?
Yeah.
Are they resistive? Is that why?
It's gonna be like 15 minutes before this computer boots.
Okay, mine will be about 3 minutes behind that.
There is you can, I'm sure there's like an instructable for 3D, you know, 3D printing. I've seen things like that.
Oh, can somebody-
A portable monitor, like a 20-inch monitor, so like, slip it in, just like
Have you
monitor.
seen the extenders?
Yeah.
The razor with the triple.
Uh,
Have you seen that? Those are my
It's my pointer.
It's like 9K. It's like it has like triple monitors, full bevel laptop.
I've seen one for MacBooks and that was just like 10 years. You can have like two.
Okay, so today got busy and I didn't prepare too much, but I thought what I want to do is I asked everybody to go through the NumPy stuff over the weekend. I actually thought it might be good for me to get an assessment. Okay, some of you guys I know and what level you're at, but what I want to do today is I'll do a little bit of a lecture, introduce NumPy and show you some stuff. I have a lab that's actually really short. I want people to just get started on that lab and try to do it during the class. And I want to go around and see what you guys are doing, and I want to look at your solution to the previous lab with you, just to get this assessment of where you are and what's going on, because I need to have a sense of your status. If I keep on giving you stuff and you can't keep up, it's not good, right? So I figured I'll do that. So just a second. Is it still logging in? Actually, should I open this? I mostly put it into Python notebook, which I hope I
and it's
What's the
directory. It's home directory, your our directory is /lab2.
So actually, so while we get started, do you have your laptops there? Okay, so what I need you guys to do is try to bring your laptops with you every day in class, because depending on the day, we might do a lab or not. I mean, I'm trying to be more regular, but today I want to do a lab, so try to bring it from now on. I know it's a little bit of hassle, I apologize, but it's just the nature of this class, we need it. Let's see. So I started out trying to write a NumPy sort of lecture, and I started out by saying that writing down some things for Python, and then I realized that I can just do it much easier in a notebook. So I just have a Python notebook that has all the NumPy stuff that I just want to sort of demo for you. You should have seen most of this stuff before, but I just want to go through it and give you a chance to ask any questions about it. And then there's a lab, so if you do log in through the regular way, you should find lab 2 now in your directory structure, okay? So you can do that while I'm talking, but this is not going to take more than like 20, 15 minutes, so we're going to switch into the lab quickly. So I didn't do very much, just a few things. I just started touching out and thinking about things you should know about Python. I mean, this is stuff that you should know by now, but we spent a couple of minutes going through it, right? In terms of basic Python data types, right, there's really 3 basic data types. There's the numbers, the booleans, and the strings. These are the most fundamental basic things, right? Now, one thing that's kind of subtle, I'm just saying this stuff because I know this will catch, you guys are going to stumble on this stuff, so I'm just mentioning it so you don't waste your time. When you say something like x equals 1, okay, internally, Python actually represents integers and floats separately. So if you say x equals 1, that's different than x equals 1 dot or 1.0, So you should be careful, because if you say 10 divided by 3 in Python, will give you 3. But if you say 10 dot divided by 3, it gets 3.33, okay? So that's something I'm just pointing out some simple things that you could suddenly get stuck on. Like, I've had code that I don't understand why it doesn't work, and it's just because some division is just giving me 0 because I'm using integers, okay? So that's a common thing that happens. Typical operations, right, plus, minus, multiply. To the power is 2 stars, right? Some languages is the caret with 2 stars. And then there's no plus plus and minus minus, but there's plus equals and minus equals, so that x equals plus equals 1 will increment x by 1, right? Booleans, the difference from C is they're capitalized, true and false, or capital true, capital false. So you have to. And then there's operations like, so in C you do and, or you have ampersand, whatever. It's all words here. So it's and or not. And XOR is actually not. It's a exclamation mark equal sign for XOR if you ever have to do that. Okay. For strings, you can use single or double quotes. It doesn't matter. But if you want to nest a string and still inside of another, so you can do double quotes and then single quotes inside. If you want to have a string inside of a string or something. That sometimes comes up, and in fact, that's going to come up in some of the configuration that you'll do for the packages we'll use in this class. But I would sometimes require you to put nested strings inside. Okay, so I'm just pointing out these little things. You'll see, with double quotes and single quotes inside, and that's what's going on. Nice thing is that strings also can do operations like plus and equal. So you can say, last name plus first name. Last name plus space plus first name will give you the full name, first name, last name. Just simple things like that. So those are basic objects, and there's their container types, and there's several container types. There's lists and tuples, and lists and tuples are somewhat similar. A list can hold any object. So here I have numbers and strings and booleans. It can hold any object. So just including another list. And in fact, how we do n-dimensional arrays, just in pure Python, is lists containing lists, and depending on how many dimensions you want to go. But that doesn't have to be regular, so you got to be kind of careful, because the first element could be a list of lists, and the second would be just a number. And so that structure, the fact that it's a coherent structure is something that you do by hand. It's not enforced in any way. A tuple is like a list, except that everything in that tuple has to be of the same type. Okay, and we can't hold lists. Okay, so it's a more simple thing. Everything is zero indexed, so the first thing is zero. If you ask for, if you have 10 numbers, if you ask for so the, if there's 10 items in the thing, you say length of the list, it'll give you 10, and the first one is 0, and the last one is 9. You can add lists, so you have two different lists, and you can add them together, it'll just concatenate them. You can ask for its length, those type of things. But there's also methods where you can add things to lists. You can put things on the list by saying, and you can pop things off of the list. So you can extend and shorten the list as you need. Okay? One of the things that you should get very comfortable with, and you guys saw this with NumPy, but this also works for most part very similar for just regular Python objects, is slicing. What I mean is that if I have a list and I want to get a subset of it, right? So if I have a list of a bunch of objects and I want the elements 1 through 3, I'll say 1:4. Okay? So start at the first one and end at the one before that, right? So 1, 2. Or if I want from the second one onwards, I say 2:. Okay? Or if I want everything up to the fourth element, I'll say 4:. Okay? That make sense? Or if it's a two-dimensional thing, can't see the comma. Oh no, I say it's 4. Or if I want to do it, you can even do it backwards in counting. So you can say, I want everything but the last element. So you can start saying, if you start minusing, it starts counting backwards from the end of the thing. So I say x:(-1) means the whole thing except the last one. I did -2, 2, right? So this allows you to index wherever you need. Yeah.
Is it -0 or is it -1?
-1.
Okay.
So that's a good question. It's not -0 because it's -1 to get the. It is subtle. It's a good question. Okay. Right, and then this is this is a list of lists. This is how you can get a two-dimensional matrix. An example that I showed you guys. I actually have my remote pointer. I don't. Okay. Loops. So the range command gives you numbers between those two ranges, integers between those ranges. So I can say make a list, right, of things between range 0 and 10. Okay. So if I want to loop over it, there's different ways I can loop over it, right? One thing is that I can just go have a counter and which goes from 0 to 10 or whatever to 9, and they say things 0, things 1, things 2. That's one way of doing it. Or I can have a iterator, which will actually, because most of the time I don't care about the index, I actually want just the content of that list. I can just get that content directly. So I say so this is a list of numbers between 0 and 9 right here, right? And I say for a thing in things, what that will do is it'll do a loop. And every time it goes through a loop, a thing would be one of the items in the list thing, right? So the first time it would be 0, then 1, then 2, then 3, then 4, right? So that's, right?
So if you have a list and you use a for loop, and the list is made of things that aren't just numbers, and you could say for a thing in things, and then it would be like an integer, and then it would be a string, and then for each element of the list?
It will change the type if you need to, right?
Okay.
If you have different types of things, it'll change the type. And if you can write logic where you can even check on the type then, and say, well, if it's this, I want this type, it's a string, do this to it. If it's a number, do this to it. You can write logic like that. This is the sort of the power of Python because it's interpreted. Yeah. And I learned from Grayson that one way of doing this is to actually use a Python exception. So you would, let's say you assume a certain type, you try it. If it fails, you try the next type. If it fails, you try the next type. You can call it exceptions. That's a apparently that's okay in Python. I thought it would be ugly, but apparently that's actually safe and okay. All right. Right. So is that clear now?
Yeah, that's can't do that in other languages.
Yeah. And something else that's nice is that this again I picked up from Grayson was that if I have a list and I need both the object and the index for some reason, you can use this enumerate. So I say I, comma, a thing, and now a thing is exactly the same as before, but I is the index for it in case I need the index for some other reason. Okay, sometimes I need the index too. Okay. And then there are these list comprehension things that you can do, which there's a little bit of a long one, so let's do it piece by piece. So this gives me a list between -10 and 10, right? And then if I do this, what I want to do, let's say I want to take a square root of this, right? So I say I want math.square root of x in x. So this is basically whenever he sees x, we'll take a square root. So math is a math library. So if I want square root, anything like math, like you have to get from a math library, you say input math, and then you can say math.square root or whatever you want, right? So here, what this does is that the x in range, this, will do the same thing as what's happening there. So it'll iterate through, and x will have one value every time it goes through, right? And then I say, for that, in that, evaluate this, right? And so, with ignoring this, if I just do that, I'll call square root on every element of this and give me back another list, right? So this is a typical thing you want to do. You have some list, you want some operation to every single element, you want to get the output, right? So this is a way for you to do that. Okay? So, yeah.
If you didn't surround it with brackets, would it give you a tuple?
I don't think so. I think you need the brackets.
If you put it around with parentheses, it'll give you a tuple.
That's true. And actually, you can, the similar type of things, I didn't do it for an example, for dictionaries, and also there's a similar type of thing, okay? And then, and this is optional, but also, look, I can take a square root of a negative number, so I can just also put an if statement here. So this is doing a loop of taking the square root of any element if it's greater than 0. So you can do it all in one line without writing a loop. There's just an example here, and you can look up, but I'm just trying to demonstrate the power of doing things with list comprehensions, okay? All right, so that's a list. Dictionaries. Dictionaries are basically tables between a key and a value. The keys can be any type, the values can be any type, and you can mix them. And so it gets a little bit potentially messy. Dictionaries for me are the most useful data object because I can throw anything into it and it'll just keep it for me. So in C++ or C, whenever I need to create some data object, I would have to make a class that holds a bunch of different types of objects, and it'd be very painful to be able to, if I had some data that I want to represent, to actually have to write some class that represents that data and then fill it. With a dictionary, all I have to do is start opening up brackets. So if I wanted to, write down, start filling out data into something, I could say, my students is equal to, and I open this, and I can just have names, let's say Joe, and then I can have a tuple, or I can have another list in here, and I can say in here something like his major, I can say CS, and add additional information. So that's Joe, and then comma, I can have Gina, again, major, and whatever. So I can build a complex data object by just opening up brackets and making dictionaries or dictionaries that hold other dictionaries. So any data that you want, you can kind of stick in dictionaries and create complicated data structures. It's almost like a database, right? That you can build. Not necessarily the best thing to do for huge amounts of data, but for most of the things that we do, it's very efficient. Okay. All right. So you can hold arbitrary data. So you use the bracket to retrieve or fill. So if I make this thing, I can say y equals fruits, apple, and it'll give me back 1. Or if I want to set this to something else, I can say fruits, apple equals 3, and I'll set that to something. Okay. Now, if I said fruits, banana, this would fail. Okay, because it's not there. But I can't say fruits banana equals 5, because then I'll add an element to it. Okay? I'm just trying to logic. There is, if you say fruits.getApple, comma, some default value, what it'll do, I didn't write this up there, it'll give you back, when it doesn't find it, it'll give you some default value. So maybe your logic, you have some dictionary, you can throw your data in, and you want some logic where if that particular piece of data isn't in that particular part of the dictionary, you want some default value to come out, you can use the get mem function. If you want to delete something from a list, you just say del, okay? And then the loops work the same. So you say for fruit in fruits, you can say print fruit. So when you do this for fruit in fruits, so you have to realize is that, so there are the values and the keys, right? So the keys are like the names in this case, right? And the values are, in this case, are other dictionaries. So if I can say, my dictionary, my students.keys will give me a list of all the names, for example, right? And when I iterate, that's what this is actually doing. When I say in fruits, this thing will give me back the keys of the thing. Okay? So when I do this, I will say print. This will be apple, and then if I want to get what actually is stored in dictionary, I actually have to reference it, right? So I say fruit. This will give me 1, and this will loop over all of them. Print, fruit 1, whatever, apple 1, orange 2. Now you can, if you want, to get just to get actually to the fruit or to get the index. There's another way of doing it. This is the example of instead of so that it's dereference already or whatever this is. You actually are pulling it out of the thing, not just giving the keys. Okay. A set is, I should have pulled this, is just it's a distinct set of elements. So it's just like a list, except you can, if you put in, if you say set.append cat twice, there will be 1 cat in there. Whereas in anything else, there will be 2 cats in there. Okay, it's a unique set of elements. And these are, the other thing with dictionaries is that the order is not preserved in dictionaries. Okay, so it's built a hash to be efficient to look up things, and the order of how you put things in the dictionary is not preserved. Okay, whereas the other objects' orders are preserved, like the list order is preserved.
Okay. So the dictionary is somehow list, right? Because we can define a list like acting like dictionary.
I'm not sure what you mean.
I mean, because list getting everything, right? So we can get the first element as, for example, food, and give them list, like that.
Sure. So you can, for example, put a list as what and use a dictionary, and then give a list back as what it refers to.
So there's no way that we can define a dictionary as a list. For example, the name of
No, if I do this, it wouldn't work. If I did this, this doesn't work, right? A list just contains items, whereas a dictionary is a key and the item refers to. So it's a table of some sort. Okay, so it's a different kind of construct. Now you could go iterate into a dictionary, make a loop, and then append the items that refers to into a list. If you wanted to, you can make that loop if you want, for some reason. You can repack it into a list if you want. All right, other just little things. Functions, you guys saw, you can define a function. So one thing to realize, right, your function has a local scope. So if you, inside your function, you say x equals 1, and when you go out of the function, x is no longer exists, right? Now, if there's something global and you say x equals 1 outside, and then say x equals 2 inside your function, it'll change the global. Okay, so if you define something outside the function, you can affect it. And anything you put inside the function, nobody else can see. Okay? And then when you finish a function, you can either you can do nothing, right? And if you don't do nothing, it won't return anything. But it will return if you look for the return. So if I write the function foo, but the function does something like prints out hello or foo, and then doesn't return anything, but I say x equals foo and I call the function, x is going to come back with none because that's nothing. Actually, that's what data type that I should have said. None is a special data type, which is like null, like nothing in Python. Okay. You could also explicitly say I don't want to return anything by just saying pass. So you can write a function and just just say pass, and we'll just a nicer way of doing that. Or in case a lot of times if I'm writing a function, if I'm designing something but I haven't filled in the functions instead of function names, I'll just write a def def foo colon, and I say pass just because I haven't filled it in and I want something to be called sorted. Okay. Of course, you can return something, so whatever you want to return. And return, you can say return x, y, z, and it'll do packing. So if I write something like, def foo, whatever, x, and I return, let's say, x, like 2x, 3x, and so on, or maybe just that, then if I call foo, So I can say, you know, y is equal to foo of 1, and this will give me y is equal to the list 1, actually a tuple, 1, 2, 3, okay? Or I can say, you know, x, y, z is equal to foo of 1, and then x would be 1, y would be 2, z would be 3. Okay? So you can return multiple things, and you can either, it'll come back as a tuple, if you just give to one thing, it'll come back. And if you go in between, if I do this, then I'll complain that it doesn't match. Okay, because you can't figure out how to pack that into, into this. Okay, the other thing is, so I don't know if people are experienced at all with object-oriented programming. I'm not really going to give too much of an introduction, but you know, if you're familiar with like Fortran-style programming, right, you would write some piece of, you have some data, right, that could represent, you know, students or whatever, and you have your functions that do things, calculate their grade or whatever it is, right, that does things. You call data, you know, functions on your data. The idea with object-oriented programming is that what you do is you kind of put that together. You have an object that represents students, right? And for each student, you instantiate an object, and that holds not only the student, the data, but also the code associated with that. And that allows me to do something like I can have a hierarchy where I'll have something called a student, which may have you know, some member functions like, you know, some properties, like a student will have a name and their grade or whatever, right? And then I can then inherit from that. I can have undergraduate student and graduate student, and there's subclass of student, but I may have a different implementation of the grade function for student, undergraduate, and graduate student. So that allows me to write some piece of code on top that deals with students and says calculate grade, and I'll give it a list of students, and when it gets to the undergrad student, it calls the undergrad grade function. When it's to the graduate student, it calls the graduate grade function. So by packing the code with my data, I sort of you know, make things a little bit easier. I can write more general things at a higher level that don't have to, they just understand the abstraction of the student, and they don't have to have an if statement in them. If the student is undergraduate, then call this function. If as a graduate student, then call this function. Okay? That's the, it makes things a little bit nicer. Okay? Now, Python also has something called modules, which in a weird way, they're somewhere between these. Basically, a module is all the functions you write in one file. You say import this thing. All those things somewhat actually act like a class themselves. Okay? So Python modules, a little bit like a class. All right, so I was going to talk about NumPy, and I didn't do anything there. So let me go over here. Let's see, green tissues or something. I'll wash my hands. Dead kernel. Try restarting now. All right, so here's my little bit of a NumPy intro. So all of you guys should have read a little bit, and a lot of this is just lifted from there, but I want to just do it in front of you and mention a few things and then give you an opportunity to ask questions in case you can get something. Right? So as in anything else in Python, if you want to go to the library, you just say import. If I say, I don't know if you guys, I didn't spend my time with this. If I say import NumPy, then anytime I want to refer to NumPy, then I have to say NumPy. But that's a lot of typing, so I say import NumPy as NP. From now on, I can just say NP. Okay? Another thing I could do is I can also say from NumPy import, and I can say either star, which means import everything, or just some sub-functions that I want. And what that does is that then I don't have to say NP dot. So if I right here said from NumPy import star, anywhere I have NP, you could have just took it off. This is just basic Python. This isn't this way. All right, so then you can make an array by just taking a Python data object into it. So you can say make an NumPy array, and here I just like I'd done before in the previous exercise or whatever, I just made a 3x2 matrix, right? And I say print A, and it'll just print it out. Notice the print out is a little different than how a list usually prints out. And an array is going to have a shape, so I can ask for the shape, and it says 2 by 3. So it tells me what the shape of the thing is, right? Now I can do slicing just the same way as did before, right? So I can say give me the first row, give me the second item of, sorry, this is the second row, right? So let's give me the third item of the second row. That just gives me a number, 7. Or I can get subsets. So I say, give me all rows, but only give me the 0 to the second element. So basically, it's a submatrix, right? So it allows me to pick any part of the data that I want. And what's cool with NumPy is that you can also do assignments this way. So if let's say I have a big matrix or something, and some piece of the matrix I want to replace with some other numbers that's small, I just have to give it the right sort of indexing, and I can say that is equal to something. The sizes have to match, otherwise you get an error. But if you do it right, then you can do things. So for example, yeah.
So you're saying you could have an array that you created and you could replace a larger array, like a section of that, by just assignment?
Yeah. So it's very powerful, right? So you can, so for example, you can imagine that, I was going to, I'm going to actually going to do this, but maybe for the next thing. Imagine you load up an image, right, of yourself, and you want to, and then you have some text that you have in a different image, small, right, a caption. And you can just put it on top by just adding it, literally putting it on top and replacing something this way. And then this should be a two-dimensional array, just like this. That's it. All right. Now, here we created something by hand, but I can also just, there's all these different methods of creating different arrays, right? A lot of times we're just going to read our data straight out of some file, and I'll show you a little bit about that in a second. But in general, maybe you want to make an array of just zeros. So a lot of times, maybe I'm trying to count some stuff, and I want to store that results in some big array. I need an array of zeros. That's what I do. So a lot of times, or I want to allocate some memory. That's what I do. Okay? You can make it, an array of ones. Or you can make it any number of constants. So here's, I want it all be -1s, for example.
So when you created like the arrays of zeros and ones, it default like the little floats?
Yes.
Okay.
So one thing I didn't say is that here, in any of these comments, you can say comma d type equals, and then quotes you can say int 16, int 32, or float 32, float 16, 464, 128, or complex. You can tell and if you look up in Python or NumPy, it'll tell you all the different types. But the default, I think, is float 32. Okay, that's a good question. If you want an identity matrix, there's a 10 by 10, not identity, but identity matrix. Okay, and then you can also make random data, right? So just like you did in the first exercise, here I just did it a little bit more just to show you, right? So what I wanted to do was I wanted to make an array of a square array. Well, I want to make something that's basically, I'm going to reshape it, so I wanted to make sure that it's something that the size of it is something that's a perfect square, right? So let's say I want to make it 5 by 5 eventually. So I'll start with I say my dimension is 5, and then I don't know. Oh, I guess I want to. How am I doing this? I don't think it really matters. It's this is just a range. No, that's fine. So here I'm saying. Okay, I'm sorry. Just ignore this one. So here, what I was doing was I was making an array from off, which is -2, to d squared, which would be 25 plus off. So that would be to 23, right? So between -2 and 23, that's what I was doing. And then I overwrote it. I never doing this. But here, what I'm doing is I'm making I can ask NumPy to give me an array with 25 elements, d square elements, and that's what we'll do, right? And I say print x, and it'll give me an array just like before between 0 and 1 all the numbers, and there's 25 elements, okay? And I can do that lots of different ways. I can say, you can, for example, say, give me 25 items between 0 and 1, but in a linear progression, right, like a line. Okay? Or you can do it with a similar type of thing with like logarithmic spacing. And so this is log base e, and a similar type of thing. Or I can say, give me a grid between 0 and 5, and if I say that, you'll see what it does. It gives me something that goes like this, and then like this, if I need something. Yeah?
So you made that array up there with random numbers and stuff. So this is probably a dumb question, but next time you call up that array X, it'll be the same random numbers?
No, it won't be.
Okay.
So that's a very good question, actually. It's not a good question, no. So yeah, every time you call it, it will give you different ones. Now, if I write a program, right, when I start, I don't know what the default is, but usually what you want to do is you want to kind of control things. So random numbers are not really random, they're pseudo-random. What they're doing is, it depends on the algorithm, but basically what they do is they'll generate a series that's going to be random, but it'll start at some point. So usually you set something called random seed, and once you set, if I start a job and say, set my seed to be, and you just give some arbitrary number, and you can just set it to be some constant number, like the constant 1, or typically what happens is that they'll either use the time, or they'll read off some chord or something to give some random number, basically, to be the start of the seed. So if you have this thing, though, always have the same seed, then you always will get the same sequence of numbers generated. So sometimes maybe you're doing something, you're making random data, and your program only crashes once in a while, right? But you want to be able to reproduce that to figure out what's going on. Just always pick the same seed so you get exactly the same sort of thing happening over and over again. Because maybe the next time you run, you just won't crash because it was some really rare, unlucky case, and this will happen. So, okay.
So some random number generators have a period?
I don't think there's a period, but I don't know too much about random number generators. I haven't thought too much about it. I can tell you generically what they do is if you just think about it, if you have like a sine or cosine and just sort of pick an arbitrary thing, you can just pick a point and it'll be a number between 0 and 1 and use that as an input to the next point, and so it just allows you to, that's one way. But there's ways of getting biases in those distributions, and there are random number generation is used for encryption at times, and if the generation is not very is not done right, then people can exploit that to guess encryption keys and stuff like that. So we're not going to worry about too much about that kind of stuff, but when you get to some real science, you do have to think about the technique of generating random numbers occasionally. Okay. All right, there's that. So this is making, I called random before. Here's another way of doing random. This gives you a 5 by 5 random. And then there's the normal distribution, which is, does everybody know what a normal distribution is? Right, this is the Gaussian distribution. It's, I'm going to get the, so this is f of x is equal to e to the minus, I'll say x minus x0 squared over 2 sigma this thing squared with some normalization factor, and a normalization factor I believe is 1 over square root of sigma I c. Okay. So this is the distribution. This comes up a lot. We're going to talk about probability actually the next thing. But if I plot this function, this is a function that here is 0. It looks like this, right? That's supposed to be symmetric around 0. And so this is called a Gaussian function. And the significance here is what the sigma is the sigma is this width, and within this range of minus sigma to sigma, 68% of the area is underneath there. This is a bell curve that you're familiar with. So this is just pulling random numbers from that distribution, rather than a flat distribution. You did that in your lab last time. So here I'm doing, so if you remember the thing that I made up there was x, had 25 elements, right? But it was straight. Let's say I want to make it into a 5 by 5 matrix. You can use reshape. Well, you can ask first of all for the, so I use reshape. And so I made it by 5 to a 5 by 5 object. Of course, you can't reshape to some shape that there's not enough data for, doesn't fit, so you have to make sure that the number of items matches when you reshape. There is a transpose, it's obvious, so it'll just take along that axis and it'll transpose the numbers. So see, this and this got flipped. That's what transpose is. Basically algebra stuff. So there's a whole library of all the linear algebra stuff you want to do. So for example, a random matrix here, I made a 5 by 5, I called it x1. Now I'm calling the inverse, right? And then I can say this is the inverse of that matrix. And then inverse means that if I take the matrix multiplied by the inverse, it should give me the identity matrix, right? So let's test that. I can just say, so here's the inverse, and here, right, so that's the first print statement giving me the inverse. The second print statement is giving me the product. And I have to do a dot product between, this is the original matrix, and this is the inverse of the matrix. So I do a dot product, and if you look at this thing, it is along the diagonal is 1, and everywhere else is extremely small. This is right, that's effectively 0. So that kind of worked. Now, that is different than if I do this. This times this is not the identity matrix. This is not matrix multiplication. This is element-wise multiplication. Okay? So that's what I want. That's why I was pointing this out. All right. So the last thing I was going to show you guys is there are different ways to read and write data from NumPy objects. You can write them into comma-separated files. And if you guys looked at the that little Python notebook that I showed you guys last time, you're going to read through, it'll show you how to do that kind of stuff. Most of the time, we actually store our data in some other format called HDF5. And it's actually pretty easy to store data in there and fetch it. So I just want to represent it to you guys, just give you guys an example of it. So you can say, you can open up a file. So here what I'm doing is I import HDF5 and I say I want a new file. And here is the name of the file. And W is for write, R is for read, right? RW is read write. Okay. I always recommend you say this because if you don't say it, if the file doesn't exist, it'll create a new file for you. If a file does exist, it'll read it in read write state. And the problem with that is that if you don't have permissions, so let's say some data I'm giving you, if you just say load this file, but you don't have permissions to write to the file, it'll give you an error because it reads it in read write state. Whereas you would have, if you would just said read it in read state, it'll be fine. So if you just put R in there, it would have been fine. Okay? And the other thing is that even if it's your own file, you open it up and read write state. Let's say your program crashes. That file was opened, so it's sometimes it's in a bad state. You didn't click close right, so then your file gets messed up. Okay? So just be explicit if you're reading or writing, unless you have a reason to be able to update an existing file, and just be careful. So here, right, so I just took that X1 and I just stuck it in here, okay? And then when I'm going to read it, I open up the file, get the file. And what's kind of cool about this is that this F object acts like a Python dictionary. So if I ask for the keys, so what I did was I made a new data set, I called it my data, and I put this tensor in it, right? To get it back, I can just say, give me the keys, and list you all the keys that are there. So there's only one thing there. I can get it back by saying, give me this thing. Now what it gives back is actually, didn't give me back the data, it gives me a reference to the data. Because HDF5 is very smart. We have multi-terabyte data sets. You don't want to load it into memory. So what this does is that it gives you the reference to it, but as soon as I say I want a subset of it, it'll read it to memory and give me back the object. Right? This way you only read what you want. Right? So if you have a big data file and you want to read a little bit of it at a time, you do it this way. But if you want to read the whole thing, I can just say make the whole thing into a NumPy array. And I'll just read the whole thing and then give me back the whole thing in memory. Okay? So I just wanted to point that out to you guys. All right, so that was like sort of my basic sort of walkthrough of basic things that we're going to have to use. I didn't think it was going to take as long as it did. I guess now it's taking longer. So here's the next lab. It's actually in the things in your directories. If there isn't, please let me know. So I want you guys to work on this for next time, actually, and I mean for next time, because I want to be able to sit down and go with you. It's not long. It's actually explicitly very. Because I wanted to do it in class today, so we should be able to do it for next time. Okay? So there's basic NumPy stuff. That's the same NumPy intro that you can look at, again, just for reference. So the first thing we do is, so a lot of times the problems that we're doing are classification tasks. Okay? So that means that I'm classifying, let's say, animals, dogs and cats and snakes and whatever, right? And there may be n different classes of things that I have. So I have pictures of dogs and cats and snakes and rabbits or whatever, right? But I need to have a way of being able to keep track of those labels. I can give them indices, cats are 1, dogs are 0, whatever. But the way that actually the Keras, which is the package we use, handles this stuff is something called a one-hot technique. So imagine I have 4 different classes of things, class A, B, and C. The way I represent the different classes, right, is by putting just a 1 in an appropriate place in a list. So, for example, here, let's say this corresponds to A, B, C, D, then this is class B, this is class A, class C, class D. So this is a very common thing that happens, so I just wanted to just show it to you, okay? So you're going to manipulate these things. Now, let's say you want to do something where, yeah, I have all these subclasses, but really I want to separate it, I want to combine some classes together. So I want to combine class A and B together and class C and D together. How do I do that? And I just wanted you, so there's a trick to do it if you want to do it. What you can do is you can use reshape and sum to do this. What you can do is you can rearrange this thing, and I give you a hint, I think, of how to do it. You can basically take the whole thing and take it and put this next to each other. So you go from as I say, you go from a 4x4 to an 8x2, and then if you sum along the right axis, then you will get, the right thing. So I want you to just try it out. I mean, take this and then do some reshaping and look what it looks like, and then call NumPy times sun on it, and then try it in different ways and try to change the axis until you get what I want. Okay? So just try out different things until you figure it out. Okay? And I can tell you the answer, but I want you to just try it and figure it out. But look at the output. If it's not right, think about what it did. Look at the manual, change it a little bit until you get what you want. Okay? It's a very simple exercise, but it's an important one to just conceptually, and it's something actually we literally do all the time. Another thing that we literally do all the time is to be able to take the data and normalize it. Neural networks typically work better when their inputs are between 0 and 1. My data doesn't necessarily have to be that way. But what I just do is I just scale it down. So what I'll do is I'll figure out what the mean of my data is and what the, let's say, the RMS or the standard deviation of my data is, right? And what I can do is then I can divide by the standard deviation and shift by the mean, and that will put the bulk of my data between 0 and 1. So here we use the normal function to make here is a normal distribution between mean at 4, width of 10. Okay, I made 1,000 of those things. And you can see here the mean is, I did a good job getting 4, but it's around 4. And then you can see the minimum and maximum, right? And then so what I want you to do is then using NumPy calls, it's pretty straightforward actually to do this, to convert this. And I want you to not just put the numbers in there, use the mean of whatever function to be able to get it as you're doing it. Very standard operation, just having you practice this. Again, this is not hard, but it may conceptually take you a little bit to get, but when you get it, then you got it, and you're good. Okay? So this is really about that. This one, I just want you to, the first lab, what we did was, remember, I showed that the flat distribution is flat. Do it again with NumPy. You can do it in a couple of ways. Easier. And it's just repeating that. Okay, just doing a connection. And the very last thing, and so give this a try and let me see what happens. So we happen to have some data sitting on our cluster. Here we load up the data. So with the data they actually are loading is separate to make these data sets. This is a liquid argon TPC detector data. Okay? And that detector, what it gives you is, so let me briefly explain that detector, and then I'll show you slides and go through this stuff when with the appropriate time, but I'm just going to you guys get a sense of the data. So that detector, the way that it works is that it's a big, well, that one's actually small, but it's a vat of liquid argon, right? And when a particle comes through, what it'll do is it'll ionize the liquid argon. And so that means that it leaves, it's going this way, it'll leave ions wherever it went, right? And then we put that detector in, we put the liquid argon in an electric field, so those ions don't recombine. And we can just drift the ions to one side. So we drift it all to one side, and then we have wires situated this way and let's say this way in different orientations, which will collect those ions, those charges. And then we read those charges. And what happens is that, so let's say I'm reading it over here, let's say I'm going out over here, and here my track went through, this is my whole detector, let's say. I'm reading it over here, a track went through like this. So the charges for the track look like this. As I'm drifting it, the charge of the tracks will go towards my plane like this. And then the first piece will hit some wire here, and then so on. So if I look at the time of the arrival of the charge versus wire, what I get is a image. So let's say my wires are going this way. So I'll get an image that represents, this plane, because z is this direction. Sorry, the time direction is this way, right? And the other one is the direction. And then I'll have wires going the opposite way. So what I get out of this detector is two different projections of of 3D tracks or 3D particle interactions. Okay, that's what that looks like. We will go through this in great detail. I'm just telling you, this is the first time you can see the data. Okay. So here, these are some neutrino charge current events. I just randomly picked a file. So I load that file. Whenever you load a file, the first thing you want to do is see what's inside of it. You just look at the keys. I printed out the keys. And you can see that besides, so the features are the images I just told you about. Besides those, there's other information that I use. For example, what kind of particle it is, so you can put these things in there. So that for whatever thing I want to do, if I want to do a classification task or an energy regression task, all that stuff, the other information is here for me to use for those tasks. But the features is the real raw data that I want to use. Okay. And then I say, okay, get this thing, show me the shape. Now, if you look at it, this is the shape of it. There's 2,500 images in this one file. It's all loaded up into one tensor. The 2 represents the 2 different planes of the detector. 240 wires in each frame, and 4,096 samples in time in each of them. Okay? That's what this shape represents. And without telling you much, I want to see you guys just to look at this data, play around with it. And if I just print it, you'll see that it's mostly empty because it's a full detector, a lot of resolution. The particles went here. Most of the detector didn't see anything. You see some -1s and whatever. There's a little bit